All right, on tonight's episode of Python Papi, we're back inside our artificial intelligence course, and we're still doing our neural networks module. Let's have a look at what we went over tonight. Now, last night, if you recall, we just dived into our neural networks module, and tonight we're going to pick up where we left off. So, in effect, what we've done here is that in order to define the hypothesis function, we just need to decide and figure out what the weight should be to determine what values to multiply by our inputs to get some sort of result. And of course, at the end of this, what we need to do is make some sort of classification, like raining or not raining. And to do that, we use some sort of function that defines some sort of threshold. For example, something like the step function. This is our step function here, as you can see. Let me move down so you can get a clearer look. So we have our 1 and 0 outputs. This is our threshold line, and this is our new state here. So as you can see, it's 0 all the way up until this point here, until it reaches the threshold. Then it steps up or jumps up, becomes 1. The step function is defined as 1 if the weight is greater than or equal to 0, else 0. We can think of the line down the middle as a dotted line. It stays at 0 all the way up until one point, and then the function steps or jumps up to 1, like I explained. So it's 0 before it reaches the threshold, and then it's a 1 after it reaches a particular threshold. And so this was one way we could define what we'll come to call an activation function, a function that determines when it is that this output becomes active, changes to a 1 instead of a 0. But we also saw that if we didn't just want a purely binary classification, we didn't want purely 1 or 0, and we wanted to allow for some in between real number values, we could use a different function. And there are a number of choices, but the one that we looked at was the logistical sigmoid function. And this is the logistical sigmoid function here. As you can see, it's a bit different. It's sort of curved instead of a straight line up. The logistical sigmoid function has sort of an S-shaped curve to it. I tried to make an S-shaped curve the best I could. We can represent this as a probability. Maybe somewhere in between, the probability of rain is something like 0.5. Maybe a little bit later, the probability of rain is 0.8. And so rather than just have a binary classification of 0 or 1, we can allow for numbers that are in between as well. So you can see here, it doesn't just jump up from 0 to 1. It gradually changes along the way, and you can fit a lot more numbers in here than just 0 or 1. That's what the sigmoid function is all about. Let me see, I kind of lost my place here. Sorry about that. Okay, and it turns out that there are many different types of activation functions, where an activation function just takes the output of multiplying the weights together and adding the bias, and then figuring out what the actual output should be. Another popular one is the rectified linear unit, otherwise known as ReLU. And this is our rectified linear unit, or our ReLU. And the way this works is it just takes an input and takes the maximum of that input in 0. So if it's a positive, it remains unchanged. But if it's negative, it goes ahead and levels out at 0. And there are other activation functions that we could use as well. But in short, each of these activation functions we could just think of as a function that gets applied to the result of this computation. Hypothesis x1, x2 equals weight 0 plus weight 1 times x1 plus weight 2 times x2. We take a function g and apply it to the result of all that calculation, and this is the new one we get. So it's the same function, we just add g here to this last result here. And this is it. And then this is what we saw last time. The way of defining some hypothesis function that takes in inputs, calculates some linear combination of those inputs, and then passes it through some sort of activation function to get the output. And this actually turns out to be the model for the simplest neural networks. So as you can see, I just put it here so you can see it here by itself. We have a hypothesis x1, x2 equals some activation function being applied to our weight 0 plus weight 1 times x1 plus weight 2 times x2. Now that's why I'm leaving it for the night. Like I said, I'm going to take it piece by piece. Even though we are doing it in the TensorFlow course, I want to make sure that I fully understand the basics because they're giving me the groundwork here. Unlike the TensorFlow where we kind of dove right in. So yeah, I'm going to take it piece by piece. But of course, I'll keep you guys posted every step of the way. But for now, this is the Python Papi. You guys stay Gucci.